Okay, thank you very much, Luca, and thanks to everybody for listening in. I see we have over 300 participants, which is wonderful. More people than I usually get at a conference talk, so hey, that's good. It's a shame we're not all together in person, as everyone knows. We're suffering, but at least if we can keep talking to each other, that's got to be a good thing, right? So there you should be seeing my first slide, which is just an aerial view of my university, Trinity College, Dublin. And then I should be going on to the next slide, which says, what's it all about? Please let us know if you can't see or you can't hear, because I could be chatting away here and nobody listening. Anyway, you should be seeing this slide, which says that this is going to be, it's not going to be the typical scientific talk, I suppose. It's going to be more of a historical look back at my work on this topic, the theory of critical distances. Talking really about how I started on this, how I came to work on the theory, people who worked with me, and various developments and why they happened when they did. And the reason I decided to talk in this way was because, you know, we work away on a daily basis, we do our research, we write our papers, and our papers always describe the finished piece of work as if it was kind of obvious and logical that we did this work and we got these results. But of course, it's not logical, it's usually quite messy. And what I wanted to do was to talk more about the process by which we get to this work. Because often it's not very straightforward and logical. And the reason it's not logical is that, you know, I firmly believe that research is a creative activity, and that when we do research, we're, you know, creating new things. We're making new theories and results. If we're engineers, we're designing and making new products. And that these are creative acts, just in the same way as, you know, as an artist will paint a picture, or a poet or a writer will write something. But maybe unlike these other artists, we don't really think very much about how it all works, about what is the process. But if we don't think about it, you know, I think certainly we could work better and do better work if we thought a little bit about how to do it and how to maybe stimulate our creativity so that we can get on with it. So that's what this next 40 minutes or so is going to be about. So starting with the prehistory, that's pre-TCD history, I started my research career in Cambridge, working with the wonderful John Knott, one of the pioneers of fracture mechanics. I was very lucky to work with him and did a PhD and a postdoc about high cycle fatigue, particularly about fatigue crack thresholds and short cracks. It was very exciting to be working in that period on these things, because we were only just beginning to understand why there are thresholds in cracks. Concepts like crack closure were only just being debated and argued about. Why short cracks behaved in an anomalous way. This was something, again, we were only just discovering and thinking about. So that was all a great you know, introduction for me. And in 1983, I got a job in Dublin as a lecturer in Trinity College, and a job that I've done ever since. That's where I've always been. And I guess, you know, when I moved over to Dublin, started as an academic, I really expected that I was going to be working on those same topics forever. You know, I don't know if it's the same for other people, but you know, I just saw myself as an expert on fatigue thresholds and short fatigue crack growth. And I thought, well, that's what I can do, you know, so I should, you know, find some funding and get on with it and do some research on that. But that actually wasn't possible in Ireland in the 1980s. There wasn't very much money around, and the Irish government was only really supporting applied research. It wasn't possible to apply for basic scientific topics like those. So I certainly had to change my mind and look around. And I was lucky to get involved with a number of companies, manufacturing companies, mostly car companies like Rover and Fiat and VW and Renault. And they were making great use of these EU networks, which of course were there in those days, just as they are now, that groups of companies and universities around Europe can get together and get quite a lot of money to do a big project. And I guess I did that at the time simply because it was the only way of getting on, of buying some equipment and getting started in my academic career. But it turned out to be, fortunately, you know, a very good thing, because the big topic that those companies were concerned about at the time was notch fatigue, by which I mean, fatigue arising from stress concentration features. You have a picture of a crankshaft there, for example, classic problem in cracks growing from the corners of the crankshaft. And when I first started talking to these companies, they wanted me to study this and try and understand it better, but it wasn't really expected that we would be able to use finite element analysis, right? And, even when we were applying for funding in the 1980s, we just didn't even talk about FEA because though, we were using it in universities, the companies were of the opinion that it would never be possible to make a finite element model of something like this crankshaft, just too big and too complicated, too many elements. And of course, we all know that that turned out to be wrong because, by 10 years later, by the 1990s, all the companies were using them, but we could never have known how fast computing would come along. But when they did start using them, then this illustrates the problem that you make a finite element model and you see the contour plot on the left, you've got that little red area, that hot spot. And very often when they first made these finite element models, the stresses that they were predicting were so large as to be really impossible because they were, calling me up and saying, look, we've got stresses here that are larger than the yield strength, even larger than the UTS of the material sometimes. And yet, it's not failing. We're running these crankshafts in cars around the world, and they're certainly not failing. So, what's happening? Why can't we make a good prediction of the effect of this stress concentration? So I started working with these companies, and that was very useful because it put me in front of real problems and all the complexities of geometry and loading, which you have, which makes the problem much more difficult than that of a simple notched specimen. Okay. You can't even really define a KT factor for a shape like this wishbone that you can see on the screen there. And so there was a need to formulate the problem in a more general way so that it could be attacked from the point of view of post-processing finite element data. So lots and lots of data, of course, from an FEA, but how to interpret that, given that all we know up to now is what happens with notched specimens in the laboratory. And there was a great urgency about this, as I say, because these companies would love to use finite element, but they didn't trust it because they were getting these strange hotspot stresses coming up. Okay. So through the 1990s, I was working, as I say, on these EU network projects. Now, the projects generally were not about notch fatigue. Certainly the money that I was getting as a partner in those projects were for doing other things, for example, looking at the fatigue of spot welds and things like that. But because it was emerging that notch fatigue was the problem, we certainly took on researchers and did work in that area, even though it wasn't really in the plan, and it was not what the EU were paying for, shall we say. I also started to get funding from the Irish government. At the time, the Irish government, as I say, didn't have much money. They only wanted to use it to stimulate industry in the country. And their view of that was that there were two big things they wanted to encourage. One was IT, computing, and the other one was biotechnology. And so the only things that Irish scientists could apply for money were in those two areas. And I wasn't working in either of those areas, right? Except, okay, I said, all right, this finite element modeling has something to do with it. So I proposed and got funding for quite a few years and in the IT stream by saying that I was going to develop a computer program to predict fatigue using these notch fatigue ideas. I never did, but I argued, of course, I've got to do some practical experiments first in order to get the data to put into the program, and that lasted for quite a long time. I never did write the software, but I guess this is just typical that we have to take the opportunities to get funding where we can, and sometimes we have to be a little bit, what shall we say, economical with the truth in order to pursue our own agendas. I'm sure there's other people who have done that. So at the time, I was knocking around various ideas that were in the literature for predicting the behavior of notches, such as predicting the growth of small cracks and whether those cracks became non-propagating or continued to propagate. An idea of Rod Smith and Keith Miller that was around at the time, where they said, well, if the notch is sharp enough, it has a critical radius and you can pretend that that notch is a crack. And that was useful, and I was able to implement that on components by making some modifications, what I call my crack modeling method. So that was beginning to work for components as well. And this all worked quite well. But, you know, there is a reason why that, and, you know, notches are easy. Okay, I say that because if you think about it, if your problem is to predict fatigue from a notched specimen, very crudely drawn there by me on the right, the notched specimen only has a few parameters in it, right? It's got a depth, it's got a root radius, and those are the two main ones. It also has an opening angle, but that only really affects the stresses if the angle is quite large. And there's also a remaining section, which is rare. It is important in some cases, but not very often. So really, you've only got the depth and the angle. So it's not too difficult, looking at this rather cynically, to propose an equation that has a couple of constants in it. And you can fiddle around with the equation a little bit until it predicts the results from these experiments, because you've only got two variables, depth and radius, right? So any reasonable theory, you know, any sensible theory that occurs to you is probably going to work, and it's probably going to predict the data reasonably well. So, and you know, I think we still see this. I still see this quite a lot in the literature, that people say, "Oh, I have a theory about notch fatigue or notch fracture. Here are my results, and I can predict the effect of notch depth, or I can predict the effect of notch radius." But you have to ask yourself, are you being ambitious enough in what you're trying to predict? And really, you should try to predict a bigger range of stress concentrations, ideally also some real industrial problems, if you want to show that your idea works. Anyway, that's a comment there. So going on to the first paper that I wrote about the TCD, I wasn't calling it TCD at the time, but this paper, Geometrical Effects in Fatigue, a unifying theory, a unifying theoretical model. I wanted, actually, the first title was a unified theoretical model, but the reviewers didn't like that. They thought unified theory was too ambitious. So I had to put unifying theory. There you go. This shows how you play around with the words in these things when you're arguing with reviewers. But this was my first paper in the International Journal of Fatigue, and it came about just because I was playing around with some data that I found in the literature. Actually, a paper from Tim Topper's group, Duquesne et al. It was. And this is some of their data on the right here, looking at the effect of crack length on fatigue limit, very classic, you know, what we now call Kitagawa diagram stuff there. And I just happened to notice that this data, this curved line, could be predicted reasonably well using the stress moving away from the hot spot of the near the crack, and just using the stress at some distance away from the hot spot. Which I was calling A0 at the time, and we now call it L, but noticing that at that half of that distance, A0 over 2, if you look at the stress at that point, that stress, and you let that stress be equal to the fatigue limit of the material, then you immediately can plot this data. You have to remember to use the equation for the crack, which is the full and proper equation, the Westergaard equation. But if you do that, then it works, and there are a few other ways of doing it, which are firstly to average the stress over a larger distance, to A0, or to look at the stress as averaged over that area that I've drawn there. But anyway, I played around with this and thought, well, this is nice. This seems to predict these results quite accurately. But that was just for short cracks. But I was very lucky, because in the very same paper, this Duquesne et al. Paper, they also had results for circular holes in the very same steel. Okay, so this is the effective fatigue limit on it says notch depth here, but it's actually the radius of the circular hole that was in the material, and it's the same material. And I found that I could also make good predictions using exactly the same constant, the same distance constant. So then it becomes, you know, more exciting, because you've got two geometrically different problems, but in the same material, and the same constant is doing it for you. And I noticed also that constant A0 is the same constant as that group was proposing, and they were calling it El-Haddad's method. There was another paper by El-Haddad, Smith, and Topper at the time, where they had made the predictions by introducing an imaginary crack, and the length of that crack was also A0. So in my mind, things were kind of tying up. You get to a point where you say, this can't be a coincidence, you know, there must be something fundamentally going on underneath all this that makes these different methods of prediction all all be working, you know. Now, it was quite difficult to get that paper published, I must admit. I thought it was a good paper, and I was submitting it to several good journals, but the journals were rejecting it. Some of the reviewers were saying, oh, well, this stuff is all very obvious and well known, and I'll come back to that in a minute, but they weren't actually quoting me any previous papers that had done this same thing, but they were saying, oh, it's all obvious. Whereas other reviewers were saying it was all wrong and, you know, theoretically incorrect and couldn't possibly work. Two very conflicting views, you might think, and sometimes I got those two views from two reviewers from the same journal, you know, so obviously something strange going on there. But anyway, eventually I did get it published, and thank you to the International Journal of Fatigue for publishing it. But I think I have the last laugh, because just checked recently, and that paper has 494 citations to it, which is actually the 6th highest for any paper ever published in the International Journal of Fatigue. So in the whole history of that journal, it's the 6th best paper that they've ever published. So thank you for that. But I think we all have those experiences sometimes, some work that we know is good, but we just find it difficult to convince others. But it's worth pursuing it and sending it to more and more journals until you get it out there, I think. Now, this slide is entitled Show Us the Evidence. And it just describes where I went then with this idea. Having shown that it worked basically for one steal from one particular publication, a theory is only useful insofar as it can predict experimental results. Now, that's very obvious. It's a basic fundamental point of the philosophy of science, that theories are supposed to be there to predict results. But, you know, you find a lot of papers in the literature where people propose theories and they don't make any predictions with them. Sometimes there's good reasons for that. But in general, you know, I think it's important that a theory, interesting as it might be and mathematically elegant as it might be, is no good unless you've got some physical phenomenon that you can predict or indicate. And the power of a theory really is in proportion to how much data it can predict and how many different kinds of data it can predict. And this is just as well true for, you know, Einstein's theory of relativity as it is true for the theory of critical distances, that it's about the volume and variety of phenomena that you can predict with basically the same theory. So I set out to see how good the TCD was at predicting the fatigue limit data that we could find in the literature. And we ended up with this paper that I published with Jerry Wang, who's a PhD student of mine at the time. I think Jerry was one of these people who was funded by the EU projects with the car companies and was supposed to be working on something else, but again, we won't go into that. So this paper, we looked in the literature, we found as many results as we could, and we plotted a lot of graphs. There's just one example of one of these graphs here. This is the fatigue limit against the depth of a notch for a semicircular notch, as it happens. But we did this, and then we used our theory, our critical distance idea, and then several other notch theories that were around at the time, which are all kind of listed here in the table. And we looked at how accurate, how good we were at predicting the fatigue limit values, the individual data points. And we're plotting these in a table. So here is the percentage of all these papers that we looked at, all those individual data points, what percentage of them were accurate to within 20% on stress or 30% on stress. And I think that's an important point as well, that we wanted to set for ourselves a limit on accuracy that, you know, described whether we were being successful or not. And we chose 20%. And the reason we chose that was we said, look, there are errors here that we can't avoid. There's an error in these fatigue limit results. There's always some scatter in fatigue, and that's probably at least 10%, right? We are using finite element modeling or you know, an equation to find the stress field. There's going to be at least a 10% error on that as well. So add those up, you've got 20%. So even if our theory is perfect and has no errors in it, we're still probably going to see 20% errors in predicting the data. So if we said to ourselves, if we can get within 20%, there is no point in trying to get any better. You know, you can spend a lot of time refining a theory and making it more complicated and getting the accuracy better, but you're really chasing your tail there. So we said, look, that's our limit. We will say we're happy if we can get within 20%. And we found, you can see in the table, that these point, line, and area methods getting very high percentage success on that criterion, better than some of these other theories. And we found, and this turned out to be, continue to be true in a lot of cases, that the point method, the very simplest method, where you just look at one stress at one point, is the best, better than the slightly more sophisticated, line and area averaging method, which is something I've never really been able to explain, but is often the case. So, excuse me, I'm just having a drink of water. Losing my voice here. I hope you can still hear me. So that was our first attempt to really be systematic, look at all the data we could possibly find and ignore nothing, and try and predict everything. And it was working pretty well. At the same time, I was still working with these car companies, and we found a lovely little example of how a critical distance approach can resolve a problem. Again, a very real problem they were having in Fiat at the time. This is a wishbone component you'll be familiar with if you know anything about car components. I don't know much about car components, but I was learning. Excuse me. And the exciting thing about this one was that when they did the finite element model, there were two areas of high stress. There was this point here, and there was this point here. And this point on the left has actually the highest hotspot stress. So the maximum stress in the whole thing is here, but it wasn't failing from that. When they did fatigue tests simulating, real use, it actually failed over here from another point where the stresses were pretty high, but not as high as here. But the difference is that here you have a very sharp corner. So though the stress was high, the stress gradient was also very high as well. So the stresses fell away very quickly. So when you use the hotspot, you expect it to fail here. But when you use the critical distance approach, because you're looking at a point slightly inside the body, that's worse over here. And so we were actually able to predict the right location for the failure. And we got a reasonably good prediction of the number of cycles to failure as well. But it was a nice illustration about why you need a critical distance approach, or some kind of approach that's, as we say, non-local, that doesn't just look at the hotspot stress. Because not only can you get the numbers wrong, you can even predict the wrong place for failure. So that was a nice, say, practical example. The other thing that we were working on, the other kind of strand of all this, apart from looking at data and trying to predict it, looking at industrial problems and trying to predict those, the other strand was to try and look at the mechanism. Okay, and I guess this is another fundamental thing about science, that if you have a theory, you may well be able to predict the phenomena with that theory without really understanding why it works, okay? And these purely phenomenological models are very common, and we use them in science and engineering all the time. I mean, we use Young's modulus to predict the stress from the strain, or the strain from the stress, without worrying too much about why stress and strain are proportional. Maybe we know the science, and you could go back to the fundamental mechanism of atomic bonding, but you don't. You just plug it into the equation, right? And there are lots of equations like that we use. But people are more comfortable with a theory, with a model, especially if it's a new one, if they can understand why it works in terms of the underlying physical mechanisms. Now, to be honest, this has always been a problem with the TCD theory. It's not easy to explain why it works and why such a simple theory works. But I started doing that in 2001, and we've been plugging away at that ever since. This particular paper, which is published in the Fatigue and Fracture of Engineering Materials and Structures journal, this particular paper, I was using that method you may be familiar with called crack line loading for predicting stress intensities of cracks. And the argument is you have a body with a stress in it. You want to know if a crack's going to go through it. If you put a crack in, you can predict the excuse me, you can predict the stress intensity of that crack looking at the loads that are applied across it, or making an analogy between your actual external applied loads and a series of point loads representing that stress gradient, if you like. And by doing that, I could make an analogy between that and the line average method of the critical distance theory. And we won't go into the details, but just say we we were starting to think, ask ourselves these questions. Well, you know, why does this work? Okay, going on to the next slide. So where are we so far in the story? It's now 2001. I've been working on this critical distance idea for about 3-4 years. I've had an idea. I've shown that it predicts a lot of data, that it has some industrial applications and maybe can be linked to physical mechanisms. Now, what I didn't know at that point was this had all been done before, okay? And of course, many of you are familiar with the fact that these ideas like the point method and the line method go way back to the 1930s when Neuber and Peterson were proposing them. It had been looked at by several people in the Italian group, such as Bruno Apsori's group and Roberto Tovo. These papers are there in the literature. Professor Tanaka in Japan made the same link as I did between the stress averaging methods and the linear elastic fracture mechanics methods. So it's all kind of there, you know. Now, I'm not going to start talking about what I did that was new and different and what my contribution was. I'll leave that to you to decide what I did versus what other people did. But the moral of the story for me is don't read the literature, right? Because if I'd been very careful and read the literature and informed myself about what was already being done and all these papers, I probably would never have continued down this road, because I would have said, oh, well, this has all been done before. We won't go there, you know? So don't read the literature is the advice I give to my research students. Anyway, you can take that or leave it. Excuse me. Now, along came Luca. Around that time, Luca Susmel, who we all know very well, started working with me. And he wasn't always a famous professor and journal editor and all that. At the time he started with me, he was just a research student. And this turned out to be a very lasting, a very, very successful collaboration. Between 2003 and 2015, we published an awful lot of papers about the TCD. When Luca first started, he was just finishing his PhD on, which was on multi-axial fatigue. And then he was appointed a lecturer in University of Ferrara, and he managed to get a very nice trick going, whereby he could spend half the year with me in Dublin, and the other half of the year back in Italy doing his lectures. And he was really able to organize his time very well. I'm sure, Luca, it was awful hard work those years, and you know, fair play to you. But it did mean that he had a good chunk of time every year to concentrate on research, to do experiments in our labs, and to develop the theories. And that was why things moved along so well. So thank you, Luca. And I have to say that though my name is on all those papers, that really Luca did all the work, right? And his approach was to dig down into all the classic fatigue problems, all the things that make fatigue difficult in real components. And we know what these are: multi-axial loading, variable amplitude loading, predicting finite life rather than just predicting the fatigue limit, looking at elastic plastic problems, and so on, you know, and really, you know, attacking these problems one by one. And Luca's philosophy, I think, is summed up in graphs like this, which you see in many of his papers, where he said, okay, firstly, I'm going to show how an existing fatigue law can be combined with the critical distance theory. So it might be a multi-axial fatigue law, or it might be a variable amplitude law. We know there are quite a few of these. And Luca would show that, you know, in principle, you could use that law that already was accepted and also combine it with the critical distance idea to make predictions. And then he looked at all the data that he could find, sometimes his own experiments, sometimes from the literature, and to take an inherent, you know, an intelligent approach to this issue of error and scatter in the data. So we started with this idea of a notional 20% accuracy was good enough. Luca had the idea that it's very, you know, simple, but it's simple once you've had it, which is to say, look at the stress life curve, the Wöhler curve. There's always going to be some scatter in the data from the experiments. You can't do any better than that. You can't predict something any better than the inherent scatter that's there. And so he plotted these kind of graphs where you plot the the predicted number of cycles to failure on one graph and the experimental number of cycles to failure on the other, and hopefully they lie in a straight line. But there is also always going to be scatter, but you don't have to worry about that if that's within a scatter band, which is similar to the scatter band of your original data that you're coming from. And so again, we have a nice criterion of success. And it's very difficult to argue with a graph that has as many data points as they're on it, and they're all doing very well, you know. And I think that's really important. So you know, thanks, Luca, because your work really put the critical distance theory on the map. I probably wouldn't have done it. It was all far too much hard work for me, and you know, far too much concentration needed to get through all those different criteria. So it was great. And it was great, I think, that though we were working together, you weren't just doing what I told you to do. You know, we were a real partnership, a real collaboration. You had your own ideas, and I was trying to help with those, but they were really your ideas and your philosophy. Okay, we also expanded the idea, moving away from fatigue and moving away from metals. All my work on the TCD and in other fields that I was working on at that time had been about fatigue. And it was only in 2004 that I started thinking about static fracture problems. And that was really because I noticed this kind of data in the literature on ceramics. I can't remember why I was looking at those results. Maybe I was at a conference and somebody showed me some or whatever. But anyway, it's a fact that if you look at the ceramics results of the fracture, not the fatigue, but the fracture of ceramics, and you look at the effect of notch radius on the left-hand side here, or you look at the effect of the length of the defect or crack on this graph on the right, then you see dependencies, you see behavior which is exactly the same as you see in fatigue. So this could be a Kitagawa diagram plotting the fatigue limit against crack length, except it happens to be a diagram plotting the fracture stress of ceramics against defect size, but it's got exactly the same kind of curvature. Likewise, the notch data comes out the same. And so the critical distance theories like the line method and the point method worked perfectly with with this problem as well. So that was exciting for me to realize that. And I also looked at polymers. I also looked at composite materials. And then I had another revelation, which was that I found a 1974 paper in the composites literature, Whitney and Neusner, which is very, very well known and very, very well cited in the world of fiber composite materials. And it is exactly the critical distance theory. Again, these D values here, here we're predicting the effect of the strength of a piece of fiber composite laminate material. We're predicting its strength as a function of the size of a circular hole in it. And the data is coming down in just the same way as, again, as you see in fatigue. And these D values are critical distance values. And he's finding an optimum value 0.03 inches in this particular case. You see what's happening when the radius of the notch of the hole is large enough, you're getting down to a point where you see the full 3 times stress concentration factor, the KT factor of 3, because it's coming down to 0.3 here. Whereas if you have a very small hole, then you've got no effect at all, and you come up to 1, and all these real holes are somewhere in between. But they're using exactly the same critical distance approach. And this is a classic paper in the world of composites, but I didn't know about it. And I think most people working on metal fatigue wouldn't have known about it. And it just shows, I think, that, we all live in our own little worlds. We go to our own specialist conferences. We go to our own sessions in big conferences. We go and read our own literature. And sometimes we don't realize that the same exact theory is going down parallel lines in 2 different worlds. In this case, in the worlds of fatigue and versus fracture, and the world of metals versus composites. So it was very exciting for me to discover the strands of this very same idea in quite different areas. And for me, it was philosophically a big question about self-perception and what kind of scientist I saw myself as. Looking back, it's amazing to me that between 1981, when I started publishing, and 2003, when I was already an associate professor in Trinity College, I published 78 journal papers, but they were all about fatigue. Quite wide. I mean, I was working on fatigue of medical materials and bones and other things, not just about metals, but they were all about fatigue, because I kind of saw myself as the fatigue guy. You know, fatigue is what I know about. That's what I'm confident in writing papers and publishing them about. And so it was quite a big step for me, quite a scary step, to submit a paper in 2004 to a ceramics journal talking about fracture of ceramics, something that I didn't regard myself as an expert in. And I think it's an important step for anybody to realize, to have the confidence to go into other fields and you know, learn as much as you need to know about that field, not necessarily becoming an expert in ceramics in this case, but at least knowing enough that I could confidently say, well, I have something to say about this field. Now, the ceramics journals rejected the paper. And again, this was a paper I found quite difficult to publish. And at the time, I'm not sure if it's still true, but at the time, the prevailing view amongst ceramics people in relation to fracture was that all cracks in ceramics are Griffith cracks, as they would say. All cracks can form to LEFM. And there's no such thing as a small crack in the way we think of it in fatigue. So what I was saying was different from that. I was saying, going back to this graph, look, these small cracks here, some of them are so small that they don't affect the strength. Others don't conform to LEFM. You have to get above a critical crack size before they conform to LEFM. And many reviewers in those journals just wouldn't accept that idea, because it seemed to be, you know, a fundamental tenet for them. So I think I published that one in Engineering Fracture Mechanics, eventually one of the fracture mechanics journals. Anyway. So it was a period, you know, very exciting for me when you have a theory, when you have an idea, and you're looking around in the literature and finding again and again the same theory can work for very, very different problems, not just in fracture of metals, but contact problems, for example, fretting fatigue problems. And so it was a great period. I was publishing quite a lot, and, you know, finding, you know, one day I might be working on, you know, fracture of a polymer. Another day I might be looking at, you know, a problem of fretting fatigue, very different types of problems, and yet the same quite simple theory being applied and getting the right answer. So it's very exciting in any branch of science when a theoretical model is shown to be solving a big range of different problems. I think I'm talking for too long here. Well, we started a bit late, didn't we? But I'm going to move a little bit more quickly, because I think I'm taking too long over this talk. I guess we should certainly be finished at the very latest by 10 o'clock. So it won't take too much longer. Anyway, probably the most significant contribution, I think, in theoretical sense, was this so-called finite crack extension theory. And this came about, I'm going to just explain this to you anyway, this came about in a rather unusual way. I was giving lectures in the Politecnico di Torino because I was on sabbatical, and they asked me to give some lectures to their PhD students about fracture mechanics. I really didn't want to give these lectures because I was on sabbatical and I didn't want to give lectures. But anyway, I wanted to be polite, so I gave them. And to make it interesting, I focused on the assumptions that are present in fracture mechanics, okay? Because, you know, whenever we have a theory like fracture mechanics, we have to make assumptions, and those assumptions tend to limit the theory, the applicability of the theory, and then sometimes we have to extend away from those assumptions. So I was, you know, knocking around, talking about the different assumptions, like small plasticity, small levels of plasticity, and things like this. Long cracks, whatever. And a few days after I finished those lectures, I had this kind of eureka moment where I thought about one of those assumptions, and it's the infinitesimal crack theory assumption. I'll mention that in a minute. And then a strange thing happened, which was that I came into contact with Pietro Cornetti, who's working in the Politecnico di Torino, he still is. And he came to me and he said, look, I was at your lectures, and because of your lectures, I was thinking about this, and I have an idea. And his idea was exactly the same as the idea that I had a few days before. And so we worked on that. Nicola Pugno also got involved in that. But it was a case of, you know, two people simultaneously having the same idea. And this is the idea. Linear elastic fracture mechanics, the Griffith theory, of course, imagines an infinitesimal crack extension. it's a virtual work argument where you say, imagine the crack gets a little bit longer, what happens to the energy? But suppose it can't be infinitesimal. Supposing we force it to be finite of some definite value, delta A instead of dA, and then you have to find the energy by integrating over the period of crack extension. So you can integrate G, or which is the same as integrating K squared, and that gives fundamentally different predictions, which can include things like this one on the right here, which is the short crack effect. So say I was very excited to realize it. It was one of those moments that comes in your brain and you realize before you even write the equations down, this is going to work. This is going to extend fracture mechanics to predict the short crack effect, and it does other things as well. And so we published this paper, which I regard as quite an important one. Anyway, moving on, because I'm taking too long. The name of the TCD didn't come about until 2006. We'd been calling it various things until then. But I realized that there are a whole load of theories, mine and others, in the literature, like the point method, the line method, the imaginary crack method of El-Haddad, this finite crack extension theory that we just come up with. And they all basically use the same length constant, but in different ways. And they all give similar, though not identical, predictions. So I propose this name theory of critical distances, with distances being in the plural, to bring together all those different methods and say these are really just manifestations of the same method. Also, TCD is handy because it's the acronym of my own university, Trinity College Dublin. So that was a bit of publicity as well. It's not the only TCD. If you look around, TCD stands for a lot of things. It stands for telecache dispenser, target completion date, transcranial Doppler imaging. And my favorite is talker change detection. What is talker change detection? It's how you know that you're not talking to a robot. Okay, something that I think we would all like to know. But anyway, there are lots of TCD, so there's no point in searching literature for TCD. You have to be a bit cleverer than that. I wrote the book in 2007 as a way of getting together all these 50 or 60 papers that I'd written by then, and making a statement about what I know about this. I think books are very useful, and I think it's a pity these days that not so many of us, not so many scientists and engineers and academics are writing books. I think the main reason for that is that we don't get credit for them. Universities like us to publish papers in high impact factor journals, and of course we should, but a paper has a certain length, and sometimes it's just not enough to capture a whole field. People in industry like books. People who are starting out on a field of research like a book. But I think we need to find ways of incentivizing people to get their heads down and do the work to write books. But anyway, I also wrote it to kind of draw a line under my work and at least slow down rather than stop working on the TCD and spend more time working on other things. But I have carried on doing work on the TCD, and just a few quick examples. This is a test where we are passing a crack through the wing of an insect, and you can see the crack hitting the veins of the wing there and passing through it and being interrupted. And that's a classic example of that finite crack extension that I was talking about. We made a finite element model of that. My researcher, Jonas Schmidt, showed that the TCD could be used very nicely to predict the experimental results in that rather weird example, and we've used it for quite a lot of different natural biological materials. Trying to find easier ways to make it easier for use in industry, where sometimes you don't want to make a very fine mesh to capture the stresses near a notch. Looking at this idea we call mesh control, which is to have quite a coarse mesh, but one with constant element size. You have to trick the program a little bit to do that. But it turns out that if you do that, you can often get good results just using the hotspot stress if you control the element size as a function of L, about 3 times L actually. So it's kind of like averaging over distance similar to the critical distance. And this may make it easier for industrial designers looking at large and complex structures. I've also done quite a lot more work, published several papers looking at micromechanisms, and I won't go into this, but it basically is a case of imagining different toughening mechanisms, like the effect of a barrier here, or the effect of unbroken ligaments like fibers in a composite material, bridging the crack, modeling those in a simple way, and then seeing how the TCD can predict them. And one paper published last year in the TAFNEC journal, I imagined actually two different mechanisms operating at two different scales, because we often find this in materials that they have maybe grains and also fibers or other mechanisms operating simultaneously. And so on the left, we've got the theoretical predictions from those simple models I just showed. But here we've got actual experimental data. And the lesson in this particular case is that for a sharp crack, a sharp notch or a crack, behavior is controlled by one mechanism, which is a macroscopic one that operates at quite a large length scale. Whereas when you get to a larger radius, it flips, you get a kink in the data, it goes to the blue line, and you're now predicting it using a microscopic toughening mechanism. So two toughening mechanisms going on in the same material, but they don't control at the same time. One of them controls in some cases, and the other one controls in others. So it's just a way to, again, to dig into the mechanism. There's also been, of course, a lot of work going on by other people, some of whom are kind enough to cite my work. And last year, because it marked 20 years since my first paper, I had a look in the literature with a plan of writing a review article about all the papers mentioning the theory of critical distances. But actually, that was just impossible because there were hundreds and hundreds of them, and I couldn't even read them all. But I did mention some in a talk I gave last year in a paper to that virtual ECF conference that Francesco Iacovello and colleagues organized. Thank you very much, guys. And I was, gratified to see that there were many people who were citing my work, but taking it on in very different and exciting ways. Here's a few of the more exotic examples. This is a nanoscale silicon, single crystal silicon, very small specimen tested in an electron microscope where the critical distance is of the order of 1 nanometer, but the TCD theory works. This is on the opposite, very large scale civil engineering structures. I've seen quite a few papers where people are looking at bridges and buildings. Luca and others have been working on concrete, for example, and it works up there as well. And even using it in situations that I wouldn't have imagined it could work, which is high plasticity manufacturing operations, plastic forming operations, where these researchers are predicting fracture during a forming operation with a lot of plasticity, again, using critical distance concepts. So there are a lot of potential applications. Last few slides, there are certainly problem areas remaining, so plenty more work for people to do. There's a problem if the body that you're in has a finite size, so that the remaining ligament gets to be similar to the critical distance. And this is something that Pietro Conetti and others such as Dominique Leguillon have looked at and proposed these so-called coupled criteria, which overcome that problem. They call that finite fracture mechanics, and there are a lot of nice examples of that. There are problems in materials that have large process zones. Some materials, the process zone is similar in size to the microstructure, like the grain size, but in others, it's much larger, where a lot of microstructural elements are involved. And in those cases, it may well be that a constant critical distance doesn't always work. And again, these coupled criteria are one way of getting around that. There's certainly more to do there. And finally, a little problem we found, and we never were able to get over it, which is what we call three-dimensional stress concentrations. What I mean is, if you look at the classic notch, there's a stress concentration, but it only happens in one direction, the X direction here, right? But if you look at a problem like this, which is a welded joint, you've got a plate and you've got a bar welded to it, and you've put some welds in here, then at the corners of the welds, you have a stress gradient in two directions, right? Both directions in the plate here are directions in which, as you move away, the stress drops off very rapidly. And when we tried to use the TCD for those, we always found it was very conservative. It would give very conservative predictions. And the only theory that I have seen that works for those kinds of problems is one that Roberto Tovo came up with, the implicit gradient theory, I think it's called. He was kind enough to include me on one of his papers because they analyzed some of the same specimens that we've been analyzing and got good predictions. So that's certainly one that needs returning to, I believe. So we're nearly there. This is the last slide, and a few facts that I've discovered about myself. I think it's good to know yourself. I'm not very good at reading the literature. I don't, spend a lot of time systematically reviewing the literature before I do a research project. I don't make long-term plans. I never really know what research I'm going to do more than about 6 months in advance. I like to keep things simple, and I hate getting into complications. And you may regard these as faults. Whether they're faults, I don't know. I don't advise everybody to be like me, but I don't know. I think it's something about those things that have enabled me to get through this particular TCD theory and be moderately successful in it. So I will leave you with that thought. And that is the last slide. And thank you very much for listening.